Welcome to this video. Today, we will dive into LeetCode problem number 261, Graph Valid Tree. We'll explore the problem statement, key concepts, and approaches to determine if a given graph forms a valid tree. Let's get started. In this problem, we are given a graph with n nodes labeled from 0 to n1. The graph is described by a list of edges, where each edge is represented as a pair, u, v, meaning there's an undirected connection between nodes u and v. Our task is to determine if the graph formed by these edges is a valid tree. Now, for a graph to be considered a valid tree, it must meet two key conditions. First, it must be fully connected, meaning there should be exactly one path between any pair of nodes. Second, it must be acyclic, no circular connections are allowed. For the input, we are given the integer n, representing the number of nodes, and a list of edges connecting those nodes. The output is a Boolean value, true if the graph is a valid tree, and false otherwise. To understand this better, let's look at an example. Suppose we have n equals 5 nodes and the edges are given as 0, 1, 0, 2, 0, 3, 1, 4. The output for this input is true. Why? Because this graph satisfies both conditions for being a valid tree. First, the graph is fully connected, there exists a path between every pair of nodes. Second, it contains no cycles, no node is part of a circular path. This makes it a valid tree. Now let's consider another example, n equals 5 and edges, 0, 1, 1, 2, 2, 3, 1, 3, 1, 4. Here, the output is false because the graph contains a cycle formed by the nodes 1, 2, 3, 1. While this graph is connected, the presence of a cycle means it cannot be a valid tree. We can further explore this with another example. Imagine n equals 4 nodes and edges, 0, 1, 2, 3. The output here is false as well, but for a different reason. In this case, the graph is not fully connected. Nodes 0 and 1 form one isolated group, while nodes 2 and 3 form another. Because there is no path connecting all nodes together, the graph fails the condition of being fully connected, and hence, it is not a valid tree. These examples illustrate how the two conditions, being fully connected and having no cycles, are both essential for the graph to qualify as a valid tree. Finally, let's review the constraints and edge cases for this problem. The number of nodes, n, ranges from 1 to 10⁻⁴, and the number of edges can range from 0 to 10⁻⁴. Each edge is a pair, u, v, where both u and v are valid node labels and u is not equal to v. Additionally, there are no duplicate edges in the input. For edge cases, consider the scenario where n equals 1 and there are no edges. This is a valid tree because a single node without edges inherently satisfies the conditions. On the other hand, if the graph is disconnected or the number of edges exceeds n1, the graph cannot be a valid tree. Another case to note is the empty graph with n equals 0, which is invalid, but this case is usually not tested due to the constraints. Keeping these constraints and edge cases in mind will help ensure your solution handles all possible inputs correctly. To determine if the given graph forms a valid tree, there are two key requirements we need to satisfy. First, the graph must be connected, which means all nodes should be reachable from any starting node. Second, the graph must be acyclic, meaning it cannot contain any cycles. With these requirements in mind, we can consider several approaches to solve the problem. One option is a brute force method using either depth-first search or breadth-first search to traverse the graph. During this traversal, we would check for cycles and make sure all nodes are visited to confirm connectivity. This involves marking visited nodes and ensuring no node is revisited unless it's the parent of the current node. While this approach is straightforward, it requires manual cycle detection. Another approach is using the union-find data structure, which tracks connected components. By iterating through each edge, we can determine if two nodes belong to the same connected component, which would indicate a cycle. If not, we union their components to merge them. Both methods are viable, but they come with unique trade-offs in terms of complexity and implementation details. Using the union-find approach, we also need to check an important property: the graph must have exactly n1 edges, which is a necessary condition for it to be a tree. After ensuring this, we verify that all nodes belong to a single connected component, which confirms connectivity. This method is efficient, with a time complexity of approximately O(n), where n is the number of nodes, and space complexity of O(n), for storing the parent and rank arrays. The union-find approach avoids recursion and explicit graph traversal, making it an elegant solution. However, it does require understanding the union-find algorithm and its key operations. Another approach that could be considered is topological sorting, but this is primarily suited for directed acyclic graphs and is not ideal for undirected graphs. As such, we discard it as an option here. Ultimately, the union-find method stands out as the most efficient and straightforward strategy because it directly addresses both cycle detection and connectivity with minimal overhead. The algorithm for the union-find approach can be outlined in a few steps. First, we initialize a union-find data structure with n nodes. Then, for each edge in the graph, we check if the two nodes connected by the edge are already part of the same connected component. If they are, a cycle is detected, and we return false. Otherwise, we union the components of the two nodes. Once all edges are processed, we confirm that the graph has exactly n1 edges, which is a critical requirement for it to be a tree. If all these conditions are met, we return true. This approach is preferred over alternatives like DFS or BFS because it is more efficient and avoids the need for recursion or explicit graph traversal. It handles both cycle detection and connectivity checks seamlessly within the same framework. The trade-offs include the need to understand the union-find algorithm and its implementation details, such as the parent and rank arrays. However, its efficiency and clarity make it the optimal solution for validating a tree under the problem's constraints. To determine if a graph is a valid tree, we need to verify two key properties. The graph must be connected, meaning all nodes are reachable from any starting point, and it must be acyclic, meaning no cycles exist. The graph is represented by n nodes, labeled from 0 to n1, and a list of edges where each edge connects two nodes. First, we perform a quick pre-check. A tree with n nodes must have exactly n1 edges. If this condition is not met, the graph cannot form a tree, and we can immediately return false. Next, we create an adjacency list, which is essentially a dictionary where each node points to its neighbors. For instance, given edges like 0, 1, 0, 2, 1, 3, the adjacency list would look like 0, 1, 2, 1, 0, 3, 2, 0, 3, 1. This structure allows us to efficiently represent and traverse the graph. Once the adjacency list is built, we use depth-first search, or DFS, to explore the graph while checking for connectivity and cycles. We maintain a set called visited to keep track of nodes we've already processed. Starting from node 0, we mark it as visited and inspect its neighbors. If we encounter a neighbor that has already been visited and it is not the parent of the current node, this indicates a cycle, and we return false. If the neighbor hasn't been visited, we recursively call DFS for that neighbor. After the DFS completes, we also need to check if all nodes in the graph were visited. If any node remains unvisited, the graph is disconnected, and we return false. If no cycles are found and all nodes are reachable, we conclude that the graph forms a valid tree and return true. It's important to remember a few key insights that simplify this problem. First, the property that a tree with n nodes always has n1 edges is crucial for the initial pre-check. Second, during DFS, we track the parent of each node to avoid incorrectly identifying revisiting the parent as a cycle. This ensures our cycle detection is accurate. Third, a single DFS traversal starting from any node is sufficient to verify connectivity because it allows us to confirm that all nodes are reachable. To implement this algorithm effectively, we rely on two main data structures, an adjacency list for efficient graph representation and a visited set to track explored nodes and detect cycles. In terms of complexity, constructing the adjacency list takes O(n plus e), where e is the number of edges. The DFS traversal also takes O(n plus e), resulting in a total time complexity of O(n plus e), which simplifies to O(n) for a tree since e equals n1. Space complexity is dominated by the adjacency list, visited set, and the recursive call stack, all of which are O(n). Here's the Python implementation of the algorithm. First, we perform the pre-check to ensure the number of edges is exactly n1. If not, we return false. Next, we build the adjacency list using a default dict. For each edge, u, v, we add v to the list of neighbors for u and vice versa. Once the adjacency list is ready, we define a recursive DFS function. This function marks the current node as visited and iterates through its neighbors. If a neighbor is the parent, we skip it. If the neighbor is already in the visited set, it indicates a cycle, and we return false. Otherwise, we recursively call DFS on the neighbor. The function only returns true if no cycles are detected during the traversal. Finally, we initiate the DFS from node 0, passing -1 as the parent since it has none. If the DFS detects a cycle, we return false. After the DFS completes, we verify connectivity by checking if the size of the visited set equals n. If all nodes were visited and no cycles were found, we return true. Let's consider some examples. For a graph with 5 nodes and edges, 0, 1, 0, 2, 1, 3, 1, 4, the function returns true because the graph is connected and acyclic. However, for edges 0, 1, 1, 2, 2, 3, 1, 3, 1, 4, the function returns false due to the cycle between nodes 1, 2, and 3. Key edge cases include disconnected graphs, such as n equals 4 and edges 0, 1, 2, 3, which fail the connectivity check. A single node graph with no edges is a valid tree, but an empty graph with n equals 0 is not. These examples highlight the robustness of the algorithm and handling a variety of inputs. To determine if a graph is a valid tree, we start by understanding 2 key conditions. First, a valid tree must have exactly n1 edges, where n is the number of nodes. This is a fundamental property of trees, as having fewer or more edges would either leave the graph disconnected or create cycles. So, we check this condition up front by comparing the length of the edges list to n1. If this condition fails, we can immediately return false. Next, we need to verify that the graph is connected, meaning all nodes must be reachable from any starting point. To do this, we first construct an adjacency list representation of the graph using a default dict. This makes it easy to iterate over the neighbors of any node. For every edge in the input, we add the connection in both directions, ensuring the graph is undirected. Now, to explore the graph, we initialize a set to keep track of visited nodes and use a breadth-first search (BFS) approach, starting from node 0. We add node 0 to the visited set and enqueue it to begin the traversal. As long as there are nodes in the queue, we continue processing them one by one. For each node being processed in the BFS, we iterate through its neighbors in the adjacency list. If a neighbor has not been visited yet, we mark it as visited by adding it to the visited set and enqueue it to explore later. This ensures that all reachable nodes are processed. Once the BFS completes, we check if the size of the visited set equals n, which would mean every node in the graph was reachable and hence the graph is connected. If this condition holds, the graph satisfies both the necessary conditions of a valid tree, having exactly n1 edges and being fully connected. Therefore, we return true. Otherwise, we return false, as the graph fails to meet one or both conditions for being a valid tree. Here, we start by importing the necessary classes from the Java library. The valid tree method is designed to check if a given graph is a valid tree. To do this, the first condition we verify is whether the graph has exactly n1 edges, which is a fundamental property of any tree with n nodes. If the number of edges is not equal to n1, we can immediately return false. Next, we construct the adjacency list representation of the graph. Using a hash map, we create an empty list for each node from 0 to n1. Then, for each edge in the input, we add its 2 endpoints to each other's adjacency lists, establishing the bidirectional connections. After building the graph, we initialize a hash set to keep track of visited nodes. To ensure that the graph is connected, we perform a breadth-first search (BFS) starting from node 0. We use a queue to manage the BFS traversal, adding the starting node to both the queue and the visited set. As we process the BFS traversal, we continue by polling nodes from the queue one by one. For each node, we iterate over its neighbors in the adjacency list. If a neighbor has not been visited yet, we mark it as visited by adding it to the visited set and enqueue it for further exploration. This process ensures that we traverse all reachable nodes in the graph. Once the BFS completes, we perform a final check to determine if the graph is fully connected. A valid tree should have all its nodes visited during the traversal, so we verify this by comparing the size of the visited set with n. If all nodes are visited, we return true, confirming the graph is a valid tree. Otherwise, we return false, indicating that the graph is either disconnected or does not meet the criteria of a tree. To determine if the graph forms a valid tree, we start with the input where n equals 5 and the edges are provided as 0, 1, 0, 2, 0, 3, 1, 4. The first step is to check the number of edges. A valid tree must have exactly n1 edges because a tree with n nodes and no cycles will always have one fewer edge than the number of nodes. Here, n equals 5, so n1 equals 4, and since the input contains exactly 4 edges, this condition is satisfied. Next, we build an adjacency list to represent the graph. This list helps us efficiently traverse the graph. Starting with an empty dictionary, for each edge, we add the nodes to each other's adjacency lists. For example, adding the edge 0, 1 gives us graph equals 0, 1, 1, 0. Repeating this process for the other edges, we end up with the adjacency list graph equals 0, 1, 2, 3, 1, 0, 4, 2, 0, 3, 0, 4, 1. This adjacency list now fully represents the graph structure, and we can proceed with checking the graph's connectivity. Now that we have the adjacency list, we need to verify that the graph is connected. To do this, we perform a breadth-first search, or BFS, starting from node 0. We initialize visited as a set containing just 0 and q as a deque with 0 as its only element. During BFS, we repeatedly dequeue a node, visit its neighbors, and add any unvisited neighbors to both the visited set and the queue. For the first step, we dequeue 0 and visit its neighbors, 1, 2, 3, adding them to visited and queue. Now, visited equals 0, 1, 2, 3, and q equals deque 1, 2, 3. Next, we dequeue 1, visit its neighbor, 4, and add it to visited and queue, resulting in visited equals 0, 1, 2, 3, 4, and q equals deque 2, 3, 4. Nodes 2, 3, and 4 are dequeued in sequence, but none of them have unvisited neighbors, so the BFS ends. At this point, visited equals 0, 1, 2, 3, 4, which includes all 5 nodes. Finally, we verify that the size of the visited set matches the total number of nodes, n. Since len visited equals n, 5 equals 5, the graph is connected, and we conclude that the input forms a valid tree. The output is true. In another example, we are given n equals 5 and edges 0, 1, 1, 2, 2, 3, 1, 3. Again, we start by checking the number of edges. Here, the number of edges is 4, and since 4 equals n1, this condition is satisfied. Next, we build the adjacency list. Starting with an empty graph, we add each edge. Adding 0, 1 results in graph equals 0, 1, 1, 0. Adding 1, 2 updates it to graph equals 0, 1, 1, 0, 2, 2, 1. Adding 2, 3 gives graph equals 0, 1, 1, 0, 2, 2, 1, 3, 3, 2. Finally, adding 1, 3 results in graph equals 0, 1, 1, 0, 2, 3, 2, 1, 3, 3, 2, 1. This adjacency list now fully represents the graph structure. To check connectivity, we perform a BFS starting from node 0. We initialize visited equals 0 and q equals deque 0. First, we dequeue 0 and visit its neighbor 1, adding it to visited and q. Now, visited equals 0, 1, and q equals deque 1. Next, we dequeue 1 and visit its neighbors 2, 3. Both are added to visited and q, so visited equals 0, 1, 2, 3, and q equals deque 2, 3. Then, we dequeue 2 and visit its neighbor, 3. However, since 3 is already in visited, we detect a cycle. A valid tree cannot contain cycles, so we conclude that the graph is not a valid tree. The output is false. In another example, we consider n equals 4 and edges 0, 1, 2, 3. Here, the number of edges is just 2, which is less than n1. Since there aren't enough edges to connect all the nodes into a single connected component, the graph cannot be a tree. The output is false. To analyze the time complexity of the valid tree function, we can break it into individual steps. First, there's the edge count check, where we compare the length of the edges list to n1. Calculating the length of the edges list is an O(E) operation, where E represents the number of edges. In a valid tree, E is equal to n1, so this step simplifies to O(n). Next, we construct the graph using an adjacency list. This involves iterating through all edges and appending neighbors to the list. Since each append is an O(1) operation, and we process all E edges, the total time complexity for building the graph is also O(E), which again simplifies to O(n) for a valid tree. Finally, there's the BFS traversal. Here, we visit each node exactly once, which takes O(v), where v is the number of nodes. Additionally, we process each edge by iterating over the adjacency list, which takes O(e). Combining these, the BFS has a time complexity of O(v) plus e. Next, we consider the final check in the function, which ensures that the number of visited nodes equals the total number of nodes. This comparison operation is O(1). When we combine all the steps, the time complexity is dominated by the graph construction and BFS traversal. Since the number of edges, e, is equal to n1 in a valid tree, the total time complexity becomes O(e) plus v. Substituting e and v with n, the overall complexity simplifies to O(n) plus n, which is O(n). This linear time complexity is efficient for analyzing the structure of the graph. Now we turn to the space complexity of the valid tree function. The first component is the adjacency list, which represents the graph. This structure uses a dictionary where each node maps to a list of its neighbors. For a graph with v nodes and e edges, the adjacency list requires O(v) plus e space. Since e equals n1 in a valid tree, this simplifies to O(n). Next, the visited set, which keeps track of traversed nodes, requires space proportional to the number of nodes. In the worst case, all nodes are visited, so this takes O(v) or O(n). Finally, the BFS queue temporarily holds nodes during traversal. In the worst case, the queue can store all nodes in the connected graph, which also requires O(v) space. When we combine these components, the adjacency list dominates, resulting in an overall space complexity of O(v) plus e, or O(n). The total space complexity simplifies further to O(v) plus e, which is O(n) plus n, or simply O(n). Comparing this approach to a naive method for validating a tree highlights its efficiency. A naive approach might involve multiple DFS or BFS traversals to first check for cycles and then verify connectivity. For dense graphs, this could result in a time complexity of O(n) squared. In contrast, the current approach optimizes this process by combining cycle detection and connectivity checks into a single BFS traversal. By leveraging the properties of trees, such as having exactly n nodes and n1 edges, the algorithm achieves a much more efficient time complexity of O(n). This makes it optimal for solving the problem. Finally, let's examine the best, average, and worst cases for this algorithm. In the best case, where the graph is sparse or trivially a tree, for instance, a single node with no edges, the algorithm terminates quickly after the edge count check. This results in a time complexity of O(1). For average and worst cases, the algorithm must construct the adjacency list and perform BFS traversal. Since the number of edges is always n1 in a valid tree, the time complexity remains O(n), regardless of the input size. The big O notation is supported by the fact that each node and edge is processed exactly once due to the adjacency list. Memory usage is similarly linear, as it depends on the number of nodes and edges stored in the adjacency list and auxiliary structures. This ensures both time and space complexity are O(n), making the solution robust and efficient. When working with graph problems, there are a few common mistakes that can trip you up while determining if the graph represents a valid tree. First, it's important to remember that a tree must be both acyclic and connected. Simply verifying one property without the other can lead to incorrect conclusions. For instance, just because a graph with n1 edges looks like it might be a tree, you still need to confirm it has no cycles and that all nodes are reachable. Additionally, edge cases often get overlooked. Small graphs, like those with 0 or 1 node, or even disconnected components in larger graphs, require special handling to avoid errors. Another common issue is in cycle detection. If you don't properly mark nodes as visited while traversing the graph, it can lead to infinite loops or false positives. For example, using DFS without tracking the parent node can make a valid edge look like a cycle. These mistakes can be avoided with careful attention to detail and thorough testing of edge cases. Another mistake to watch out for is making incorrect assumptions about the edge count. While it's true that a valid tree with n nodes has exactly n1 edges, this alone is not sufficient to conclude the graph is a tree. For example, extra edges could introduce cycles, or fewer edges might leave the graph disconnected. Furthermore, inefficient implementations can be a major pitfall, especially on larger inputs. A brute force approach, such as checking connectivity for all pairs of nodes, or using an adjacency matrix for sparse graphs, can lead to performance issues. Adjacency matrices, while straightforward, consume n² space, which is unnecessary for graphs with far fewer edges. Optimizing for efficiency is key to handling real-world scenarios and large problem sizes effectively. Understanding the unique properties of trees is crucial in interviews. One key property is that every tree connects any two nodes with exactly one path, which ensures the graph is both connected and acyclic. This is why a valid tree with n nodes always has exactly n1 edges. To work efficiently, you should be comfortable using adjacency lists for sparse graphs and adjacency matrices for dense ones. When it comes to algorithms, both BFS and DFS are popular choices for checking connectivity and detecting cycles. However, union find, or disjoint set union, is another powerful tool, particularly for undirected graphs, as it can efficiently handle both tasks. Finally, always clarify the input format with your interviewer, including details like whether the graph is directed or undirected, or if nodes are zero-based or one-based. These assumptions can significantly impact your approach to solving the problem. Exploring related problems can deepen your understanding and help you apply similar concepts across different scenarios. LeetCode 261, the core problem for determining if a graph is a valid tree, builds the foundation. LeetCode 200, the number of islands, involves checking connectivity within components using DFS or BFS, which is conceptually similar. LeetCode 323, the number of connected components in an undirected graph, focuses specifically on identifying disconnected parts of a graph. Finally, LeetCode 684, redundant connection, requires detecting cycles in an undirected graph, often with the help of union find. These problems highlight different aspects of graph traversal and connectivity, making them great practice to reinforce your skills. When choosing an approach to solve graph problems, it's essential to weigh the trade-offs. DFS and BFS are straightforward methods for checking connectivity and detecting cycles. While they are simple to implement, they have a time complexity of n+e, which can be slower for very large graphs. Union find, on the other hand, provides a more efficient solution with an amortized time complexity of alpha n, where alpha is the inverse Ackermann function, which grows extremely slowly. This approach, however, requires extra space for maintaining parent and rank arrays. Alternatively, you can use edge count and degree checks to quickly verify if the graph has n1 edges and is connected, but this method alone won't detect cycles, so it needs to be combined with another technique. Each method has its strengths and weaknesses, so the best choice often depends on the problem's constraints and requirements. Great job! You've now learned how to approach the graph valid tree problem. Remember, a valid tree in a graph must be both connected and free of cycles. Try similar problems to strengthen your understanding. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!